Okay, October 14th, 2021. That's the lecture on Physics 37. And so just for an announcement here you go. I corrected the second lab report, the report for the second lab. Check it carefully. Some of you didn't do well. I want to make sure that you do well in the next report. Okay, and what else? Okay, so we're going to continue with Newton's law for circular motion. Applications of Newton's law. Continue with applications of Newton's law. Okay, so here you go. Let me show you. We're not going to do every example here in my notes, okay? We cannot do every example here in my notes because we're running out of time. But I encourage you to solve all those examples that I have in there. Okay, so here you go. We did this example here. The car in a curve. Okay? And then the next one that we have here is the case of a banked curve. It's an important problem too. Okay, in the case of the banked curve, you don't need to have friction between the tire and the pavement and to negotiate the curve. And there's a reason for that. The reason is that because when you have a banked curve, the normal can be broken down into a component that's vertical and another component that's horizontal. And it is the horizontal component of the normal here that acts as a centripetal force in the car. So if you have an oil spill here in this banked curve, and you have the proper speed as well, you may be able to negotiate the curve safely. Okay? So even though you don't have any friction here on the pavement, you may be able to negotiate this curve safely. Have you ever seen a banked curve out there? In the freeway, in the exits of the freeway? Okay? Okay, so sometimes they do something strange, the curve is to the left and they bank the curve to the left, right? But then sometimes they made the mistake that you have a curve to the left and they bank the curve to the right. I have seen that happening, okay? Even the freeways out there. And some races, in Formula One race, they came up with a situation like that in one of the race tracks there. The pilots, the Formula One pilots were not happy with that. Okay, so they make those mistakes. Engineers make those mistakes. They don't do that all the time, but sometimes they do this mistake. Okay, it's not safe to have a curve banked to the right when you're supposed to make a curve to the left. Okay, the curve must bank in the same direction that you're doing the curve, right? That you're. So let's solve this problem. Let's say a car of mass m is undergoing uniform circular motion on a banked curve of radius r. There is no friction between the tires and the surface. What must be the angle of the banked curve so a car traveling at speed v can safely negotiate it without skidding? Okay? So here you go. Let's take a look at this drawing. Let me get the PowerPoint. Maybe it's better. PowerPoint. What's that? Take your time. Take your time. Here you go. Coming. Okay. Oh, he covered and saved file. Interesting. That's what we did last time, right? Oh boy, not responding. Okay, be patient. This guy doesn't want to. Well, let's while he saves this. Did he save it? No. Okay. While he saves it, let's use that drawing. So here you go. That's the situation that we have. We know. Let's see what we know the radius of the curve. We know the mass of the car. That we know that there is no friction. We know the speed, and we want to find out the angle of the banked curve. Okay, so the car can safely negotiate the curves, safely negotiate the curve. Oh, oh gosh, keep on flashing like that. Let's see what's going on here. Okay, so it saved it finally. Okay. Here you go. Okay. Before we start solving the problem, just take a look at this situation here. Suppose that we have an icy road, no friction whatsoever. We put a car here at rest. What's going to happen to this car? It's at the top of the banked curve. What's going to happen? It's going to slide down, right? Okay. So car will slide towards the center of the curve, right? But what about if the car is going very fast? You know, through a patch of oil, just like you have in those races. You know, the car is gonna shoot in a straight line, right? And shooting the straight line means what? That the car is gonna slide away from the center of the curve. The distance to the center is gonna increase. Okay, but and that's because if the car is going very fast. So what's happening here? Either the car is going to slide down if it's going too slow, or the car is going to move away from the center of the curve if it's going too fast. That tells us that there might be a sweet spot at a given speed that the car still can negotiate this curve safely. Okay? And we are assuming that there is no friction here. If you have friction, then it's even safer than that. Even safer than that, okay? So that's the idea that I want you to have in mind before we start solving the problem. Okay, so here we go. We have this situation here. We have a centripetal. We must have a centripetal acceleration. We have the weight of the car. We have the normal being applied to the car. Okay, and this component of the normal is the one that serving as the centripetal force. There is no need to have friction in this specific case. Let me see if I have here. No, okay, that's unrelated. Suppose that the car has just the right speed to be able to negotiate the curve, okay? So here you go. Banked curve problem. Okay, what you know? You know the mass, know the mass m. What you know? You know the mass m. We know what else? The speed v, the radius r, mass m, the radius r. We know that there is no friction, okay, and the radius r. Speed v, radius r. We know that there is no friction. There is no friction. Frictionless road. find the angle of the bank curve if the car were to negotiate the curve safely. Okay? That find the angle theta of the bank curve if the car were to negotiate the curve safely. So what you're gonna do, you're gonna set up Newton's laws. Here you go. Here we go. Net force is going to be equal. Well, in this case, we do not have friction, right? So you can take this one out. We have only the normal and the weight, nothing else. The normal and the weight. And we can break down this equation x and y components. Let's see if we can do that. Yep, we have them here. I'm gonna copy everything so it makes my life easier. And we can even come up with a numerical value as well. Go. We don't have friction, right? So I have to remove the friction term here. Don't have friction. Okay. Okay, now the normal has a horizontal component. And we're going to write that down as being, n. And you gotta see if it's sine or cosine. Okay, let's figure out whether it's sine or cosine. Here you go. This angle is theta. This angle must be theta too, right? This angle right in here, or this angle here. So the x component is going to be a sine of theta. Okay? Here we go. Sine of theta. What else? There is no weight along the x direction. So we can put a 0 there. I'm just emphasizing that there is no weight in there. And what else? And sub y is going to be n cosine of theta. Is going to be upwards. Cosine of theta. Huh. And here we are going to have minus mg, no 0. We find from the second equation, we find what the n is. Okay, so here we go, and there is no force of friction, right? So we have this guy here. We're gonna solve for this one. And cosine of theta is mg. Forget we want to solve for the velocity. The centripetal acceleration is what? Let's go to the next step here. I'm not even gonna solve for the normal because we don't need it. We just wanna solve for the velocity. For the velocity, not for the angle. Okay. One way to solve for the angle. Here we go. Let's write it down. V squared over r. I'm gonna use this one here. Here we go. We know V. I'm gonna highlight what we don't know, right? We do not know theta. We do not know n, right? Just highlight what we don't know. Oops. Okay, we do not know 2. We have 2 unknowns and 2 equations. So in principle, you can solve this problem. Okay, one way to solve this problem is to solve for n and replace n here at the top. That's one way to solve this problem. The other way to solve this problem is to divide the first equation by the second and solve for theta. Okay? So 2 different ways of solving the same problem. And that's the way we... Okay, I'm gonna solve for n and then plug there on the top. Okay. Here we go. Substitute that here. Oh no, I don't want to do that. I just want to copy it. Here we go. Substitute that here. It becomes tangent. Sine over cosine. Okay, and now I eliminated the other equation, right? And we can cancel the mass on both sides. Mass, mass, G. Oops. Tangent of theta becomes RG. That is there. That's how, so if you want to design the curve for a special speed, that's the Bankit curve for a special speed. That's the angle that you gotta provide to the bank. Okay. So let's come up with some numerical values. Let's see. It goes with the square of the velocity, this angle, right? So that if you want to solve for theta, you gotta do arctangent. I need to start equal. Here we go. This one. Here we go. Arctangent. And let's go to the Excel. Let's get just a single radius. We were doing for what radius of curvature last time? Last time we were using, we calculate that, right? Yeah, 664, right? Let's make less than that. You know, Excel is very useful for simulations here. So here you go. We can put theta here, and we're gonna go with the speed. We have r theta. We're gonna do 4. First, it's gonna let's put in degrees. Oh no, this one here. Here you go. Degrees. All right. Here's gonna be meters per second. Here's gonna be meters, and I'm going to use. Let's put a very sharp curve. Let's say 30 meters. And I'm going to start with a with, let's see, a very 5 meters per second. That is 5 meters per second. It's not very fast. And then 10 meters per second, 15 meters per second, and so on. And then this one here is going to be arctangent, A tangent. Okay, gotta watch for that. A tangent. What's that? It's V squared, right? Over what? Do you remember? R times G, 9.8. Then I gotta close the parentheses. I forgot to close the parentheses. Here you go. Now the parentheses. But then I'm gonna do something else too that I didn't do. We gotta, put the results in degrees, right? Not in radians. We see degrees better, right? And I'm gonna do something else too. It's not gonna be D3, it's gonna be D$3. And then as the speed increases, what's gonna happen to the angle? The angle must what? Increase, right? Okay, the faster you go, the steeper the angle is. But I'm doing meters per second. Let's translate that in terms of miles per hour that we're used to. Miles per hour, so how do you change that? We got a 5 meters per second, right? 5 meters per second is going to be, this guy divided by 1,000. It's gonna do in kilometers. Yeah, let's do kilometers first, right? And then we gotta multiply second. We gotta multiply by 3,600. What I have here is kilometers per hour, not miles per hour, but kilometers per hour. So you have a clear picture, better picture of how fast our car is going. If you want to make it in miles an hour, all you gotta do is divide by 1.6. Okay, so here we go. That's gonna be 36 meters per second. Okay, 180. Now we're going too fast, right? Here we go. 50. What's 50? Yeah, that's a lot. Okay, nobody's gonna go this fast, right? So let's make a little bit. Let's put some more values here in between. Here we go. 14 meters per second. 50 kilometers per hour. 30 miles an hour. Okay, now we have more reasonable values here for the speeds. We should go to what, to 7? Yeah, okay. That's gonna be the angle. The angle gets steeper and steeper. Okay. If you go faster and faster, you need a steeper and steeper angle, and that's your sweet spot angle, right? That's your ideal angle for you to negotiate the banked curve. If you have no friction whatsoever, if you have no friction, you have to tune the speed of your car to this speed here. Okay, you gotta accelerate or decelerate to this speed here so you don't lose control of your car. If you put some friction in there, then it becomes safer. And it's a problem that's a little bit more difficult. I have solved that. We're not going to do that here, okay? If you're going to put friction, then you're going to have, what else you're going to have? Here you go. If there is friction, if there is friction, if there is friction, then you have to account for the frictional force between the tires and the pavement. Okay? And this is going to be the direction of the frictional force. Like that. I'm going to change the color. Okay, and we gotta put the force of static friction there. The added friction is gonna add complicated mathematical difficulty to the problem. Okay, because now your friction is gonna have a vertical component and a horizontal component. Okay, if there is friction, so it's more complicated to solve. Put it here, but it's safer for the car as well. Simple enough. Let's plot it. Not this one. We're gonna plot this guy here against the angle. Look at how steep the angle becomes, 75 degrees. It's a lot, right? So that's 45. 45 degrees already steep. 75 degrees, wow, even steeper. Okay. And there is a racetrack in Belgium that's very steep indeed. Well, let's plot this equation first, and then we worry about here we go. Okay, so here we go. That's how it looks like. It's not kilometers per hour, it's miles per hour. Because I changed it to miles per hour. Here you go. Miles per hour. Oops. Angle in degrees. Okay, when it comes to 90 degrees, this, because it's a tangent function, it's gonna go, asymptotically to infinity at 90 degrees. You see the function is starting to take off. That's miles per hour, that's degrees here. Let's see if it's recording everything. Full screen, okay, good. We're in good shape. Now let's go to another one. Let's solve another problem. Oh, this one is a problem of apparent weight. Okay, you can get zero G, right, by boarding a elevator that is in free fall. But you can get some zero G too if you jump into a centrifuge like that that goes in the vertical direction, right? How do you call it, that ride that we have, the parts there? What's that? No, no, not this one. The other one that goes more slowly. Oh boy, I forgot the name. Ferris wheel. Yeah, Ferris wheel. Yeah. There is a Ferris wheel that goes in the vertical, and then there is the other one that's a centrifuge that goes in the horizontal plane and just stays stuck. Yeah, that's right. You spin. That's right, and the floor just drops out, and you don't fall, right? Because you have enough centrifugal force to prevent you from falling, right? Okay, this one is the Ferris wheel. Yeah, the Ferris wheel. So here you go. How do you can, at given instant of time, you're sitting here in the chair of the Ferris wheel at the bottom, and then as the Ferris wheel rotates, you're going to be at the top, right? And throughout the ride, okay? The ride here at the bottom and at the top, they are easier. The problem here at the bottom and at the top are easier to solve. Anywhere else in between is more difficult to solve. So we're not going to do that. We're not going to worry about that. So what happens when you are in a Ferris wheel? Here you go. Here's you sitting in the chair. Let's say you are sitting in a scale. Okay. You have the weight, you have the normal, but you are accelerated downwards at this spot. Here is all the way around. You still have the normal upwards, you have the weight downwards, but you are accelerated upwards. See the difference? At the bottom, you are accelerated upwards. At the top, you are accelerated downwards. That's the important difference between those two situations. Let's see if I have here. Here, that's the one. Same drawing. And I don't like this normal here. This normal, let me see. Okay, this normal has to be longer than the weight. That's right. You just here that the normal is shorter than the weight. Okay. So the idea is calculate the apparent weight at the top and the apparent weight at the bottom. Okay, so let's do it. Ferris wheel. Example of the Ferris wheel. Ferris wheel. Mass m, rise on the Ferris wheel in the vertical circle. The radius of the circle is r. The speed is v. Find the apparent weight of the mass at the bottom and top of the ride. This is an apparent weight problem. Okay, so you know m, r, and v. You know m, r, and v. Find n. Okay, solution. But let's see, we want to solve what at the top of the bottom of the ride. Let's see here. Find the at the bottom and top of the ride, both places. Okay, so this one's gonna be a one-dimensional problem. Let's start at the solution. Top. Okay. top of the trajectory. Just like before, we are going to have net forces weight plus the normal equal to time plus mass times acceleration. In this case, the centripetal acceleration is going to be downwards. Okay, so wait a minute. We do not have this is a one-dimensional problem. Okay, so we do not need this one here. It would become a two-dimensional problem if you have the Ferris wheel at an angle other than the top and the bottom. Okay, so we're going to have ny plus wy centripetal acceleration in the y direction. Okay, so at the top, the centripetal acceleration is the same direction as the weight. Okay, so mg here, I'm going to put minus mg. And I'm even going to put w instead of wy. You know what? Put wi there. Then has only a y component, so I can write down as being n to simplify the solution. The centripetal acceleration has only a y component, so I can take out the y subscript. And on the top of that, at the top of the trajectory, the centripetal acceleration is going to be downwards. So if I write this thing as a magnitude of the centripetal acceleration, we end up having a negative sign here. That's pointing in the same direction of the weight. Okay, and now I can solve, oh, don't forget to put v squared over r, right? V squared over r here. V squared is positive, r is also positive, and solve for n. When you solve for n, we get a weight, an apparent weight that's less than the weight itself. mg minus something else. Okay? When the centripetal acceleration is in the same direction as the weight, your apparent weight is going to be less. If it's in the other direction, right, that's at the top. If you do at the bottom, you're going to weight more. Here you go. Bottom. Same thing, n plus wy. mg is going to be negative. And now the normal is going to have the same direction as the centripetal acceleration. So here you go. Whether I put, if I put the magnitude of the centripetal acceleration here, the sign of this guy is going to be the same as the sign of this one. And I can take out the negative sign and the magnitude as well. Solve for n, and what you get is something more than your regular weight. mg plus mv squared over r. I want to do one more problem here so we can move on to the next topic, okay? That's the apparent weight problem. Motion on the wrist. Oh, I'm not going to do that, but everything is spelled out in detail. You can do that by yourself. It's the case of the skydiver problem, okay? If you're jumping from an airplane or from a static balloon, what happens to our speed as the time goes by? And here's another example of resistive force. Is a mass that's falling through a viscous fluid. Okay? And what I'm gonna do, here go. Everything here is solved in detail. And what else? This one here. Yeah, I'm not gonna do this one, but I want you to go through that. Okay, what I want to do is this one, motion in accelerated frames of reference. Every problem that you solve here, assume that your frame of reference is not accelerated. Every problem we solved so far, assume that it was resolved in a frame, in a inertial, we call it inertial frame, in an inertial frame of reference. Inertial frame of reference, not accelerated. Not accelerated. Okay, very important. Newton's laws of motion applies only to inertial frames of reference. To inertial frames of reference. So what's the definition again of inertial frame of reference? Is whether a frame of reference is accelerated or not. Okay? If a frame of reference is accelerated, if a frame of reference is accelerated, let's see, if your object is inside a frame of reference that is accelerated, okay, comma, Newton's laws do not apply. Okay, so you must solve your problem using a different frame of reference that is not accelerated, that is inertial. Okay. However, even though Newton's law do not apply for non-inertial frames of reference, however, we still can use it provided you adjust the laws of Newton. Okay. However, you still may be able to use Newton's law in a non-inertial frame of reference, provided you adjust Newton's law. Newton's law. Okay? Provided you adjust Newton's law. And let me show you how you do that. Save it. Let me see. Oh, I don't have an illustration here. Yeah, unfortunately I don't have an illustration here. Okay, maybe I have here in my notes. Okay, so here you go. The case of a train that is accelerated. We all experience that even inside our cars. We don't need to be inside a train, right? You go ahead, get a plumb bob. Okay, a string attached to a mast there at the end, the same one that we used there in the experiment, right? Just imagine what happens when you accelerate your car. When you accelerate your car, your plumb bob is going to get out of the vertical. Not only that, but you also feel a force, sort of a force propelling you backwards, right? Everybody has had this experience, right? If you slam the brake of your car, then you feel a force propelling you forward, right? You accelerate, you feel a force propelling you backwards. You slam the brake of your car, you feel a force propelling you forwards. That's because you are inside the non-inertial frame of reference. You feel that force. That force we call a fictitious force. Okay? Newton's law cannot be applied in a frame of reference like that, but we can make adjustments to Newton's law to account for the fact that your frame of reference is accelerated. Okay, so let's write it down. In a non-inertial frame of reference, in a non-inertial frame of reference, one that is accelerated, such as your car when you are accelerating it, Newton's law of motion need to be adjusted. And how do we do that? Needs to be adjusted. How do we do that? You know, needs to be adjusted by accounting for a fictitious force that you feel when the frame of reference is accelerated. Okay, this fictitious force we also call the Einstein force. Okay, Einstein studied this type of problem, so we give it a name, Einstein force, as well. So let me see if I have another PowerPoint that has this illustration. It's better if I can get it. P37. This one is P120. I want the P37. Nope. Okay, let's try another one. Nope. Let's see. Oh, that's the one I want. Hopefully I have it. It has what I want. P37. Where is it? Huh. No longer there. P37. Must be this one here. Nope. Huh. Interesting. Let's try it again. Bear with me. Open. Folders, that's what I want. Lecture. That's the one I want. Let's see if it goes. Oh, okay. It didn't open there, maybe it's open here. Let's see if the illustration is in there. Oh no, that's too much. Okay. Yeah. Okay, it doesn't have it. Okay, I'll have to use that that drawing there. Okay, so here you go. Let's take a look here at this drawing. Okay, so the case of the train that's accelerated, here you go, accelerated to the right. Here you go. We have what? We have this tension you have the weight, and then we have the fictitious force that always appear contrary to the direction of acceleration. If you know that you are being accelerated to the right, you can solve your problem in your non-inertial frame of reference by accounting for this fictitious force. So instead of putting net force equal to ma, you put net force equal to 0. Okay? And the net force is going to be the tension, the mg, minus the mass times acceleration of the frame of reference. Okay? So here you go. Here you go. The fictitious force, this fictitious force, will always be contrary to the direction of the referential. It will be always in the direction, always in a direction opposite to the acceleration of the frame of reference. Okay. So Newton's law is written the following: Newton's law, Newton's second law, ends up being written in the following way. Okay. Still net force is going to be equal, in that specific case, right, to the train, tension plus weight minus the mass times the acceleration of the referential, equal to 0. Okay, that's the fictitious force here, and that's how you're going to that's how you usually solve the problem. It works in, you know, in every case that we have done, that we do. Okay, so basically that's what I want to do. Let me take attendance here, where we came to the point where we can take our break. Let's see, raster attendance. Oh, not showing. Why this one is not working? Okay. Okay, today is the 14th. Daniel Abram? No? Mario Acevedo Jimenez?
Yes.
Okay, Arun Atif? Musa Atif? Genesis Bell? No. Jennifer Camarillo? Okay, Vincent D'Aloisio? Robert Faust?
Here.
Pedro Flores? Lawrence Flores?
Here.
Alexander Garcia? Sung Ham? Brian Herrera? No. Brian Inez? Athena? No. Jesus Lepp? Cassandra Martinez? Not here. Dylan Martinez? Henry Martinez? Leonardo Melgar? No. Rafael Mercado? Raymond Miramontes? Okay, Raymond, not here. Jaime Mondragon? Okay, Alexis Nigret? Marco Antônio Partida? Armando Pérez? Abraham Pérez? No. Nicolas Pisano? Hans Pusser? Stop coming, right? Ramon Quintana? Albert Ramirez? Ali?
Yes.
Sharabi? Okay, Davidson Paxley? Antonio Vega? Kenneth Villagomez? There. Okay, Patrick Villavazov?
Yes.
Nolan Williams. Okay, so let's go ahead and take our break. Let's see what time is that. 5:50, right? So let's go 5:50 to break till 6:05. 6:05 p.m. And let me take a. I'm gonna pause here. Remind me to turn on again. Okay. Okay. So okay. In physics, we have this idea of work that's completely different from the verb work. Okay. There is not a verb. Work in physics is not a verb. It's a noun. Okay. And the idea of energy is closely related to the idea of work. Okay. And so what I like to do, here you go, the concept or idea of work and energy. And energy. You know, when the books define work and energy, they don't define it well. Even Wikipedia. Okay, let me show you how they define those things out there. I have seen that over and over again. They never fix this problem. You know, think about that. You are looking for a definition of A, right? Think about that. You're looking what's the definition of A, and then you go to the encyclopedia or go to your dictionary, and the dictionary says, okay, A is B, right? Okay, if you know what B is, you resolved your problem, right? But if you do not know what B is, you go back to the dictionary and then look what means B, right? And then what do you find in the definition of B? You find the definition of B that B is A. Okay, didn't help you, right? And that's what Wikipedia and other books do with work and energy, okay? They define work in terms of energy, and when you go get the definition of energy, they define energy in terms of work. Doesn't doesn't help at all, right? So Wikipedia does that, other books does that too, okay? So I came up with my own definition, okay? So for my students to understand the concept. Let me see if I remember that by heart. Here you go. First, we start. It's easier to define energy first, okay? Energy is a concept in physics. Is a concept in physics that is related to the effort of doing a given task. Okay, that's what energy is all about. Well, now you gotta define what a task is, right? Here you go. One possible task. Examples of tasks, right? Move this bottle from one place to another. Right? Raise this bottle against the acceleration of gravity. Those are examples of tasks. Okay. So a given task is defined as being something. Let's see. One example. Let's put it this way. One example of task, right? One example of task: moving an object from from one place to another. Okay? That's one. So now we got the idea of energy sorted out, right? So in order to move this bottle from one place to another, we need a given amount of energy. If you have this given amount of energy, you'll be able to move this bottle from one place to another. If you don't have it, that amount of energy, you won't succeed. Okay? So what about work? Okay, work is a quantity defined. Let's see, work is related to the amount of energy that you need to perform. Let's see, work is Yeah, it's the amount of energy that you need to perform. I had a better definition. I don't remember right now how it is. But we can leave this way. Work is related to the amount of energy that you need to perform a given task. Okay. Let's see here. Let's see. You're considering for doing right a given task that you require to perform a given task. Okay. And the best way to define work is in the mathematical sense. Okay, mathematically speaking is like that. We define work in the following way. Here you go. Suppose that we have an object and you apply a force to this object for the object to move from one place to another. Okay? So by making this object moving from one place to another, you did some type of work in this object. And mathematically speaking, the definition of work is, let's see, right down, here you go, is given by this equation here. It's the force multiplied by the displacement and multiplied by the cosine of the angle between the force and the displacement. That's how we define work. Okay, so here you go. Let me show you. We don't have it here. Okay, work and energy. Here you go. So suppose that you have an object sitting here at a place, and then you apply a force to this object, and this object moves from one point to another. Okay? We can define the work done by this force. The work done by this force is going to be the force times the displacement and the angle and the cosine of the angle theta. That's how we define the work done by a given force. Okay? So if you have a force of 1 Newton, and this force of 1 Newton, and this object is displacing 1 meter, the work done by this force was 1 Newton times 1 meter. The angle here between the force and the displacement is going to be 0. Okay? That's the mathematical definition of the work done by a given force. The work is defined in terms of a force, of a given force. It doesn't have to be this force F, it can be any force. So let's say work done by this force here is 1 Newton times meter. But what about the work done by this force here that you see, the mg, the weight? Okay? So there is an angle of 90 degrees between this force and the displacement vector, right? So what's the cosine of 90 degrees? Cosine of 90 degrees is the work done by this force is going to be mg delta x times cosine of the angle between them, right? What's the angle between mg and delta x? 90 degrees. What's the cosine of 90 degrees? Is 0. Okay? So every force that's perpendicular or normal to a given displacement, there's no work whatsoever. Okay? Can you picture that? Here you go. If the force F has an angle theta, then the work is going to be what you saw before, right? The force delta x cosine of theta. Let's see another one. Normal. What's the work done by the normal force in this case? What's the work done by the normal force in this case? 0, 2, right? 90 degrees. Okay? And so on. Okay? What about the force of friction? You have this object moving from one place to another, and we had this force of kinetic friction being applied throughout the whole displacement of the object. you know, what is going to be the sine of the work done by this force of friction? Look here at the angle, right? The angle is 180 degrees. Yeah, it's going to be negative. Okay, cosine of 180 is minus 1, right? So the work done by the force of friction is going to be a negative work. Depending on the value of the force of friction, it's going to be the value of the force of friction times delta x times minus 1. Make sense? Any force that goes against the displacement of the object has a negative work value. Has a work value that's negative. Okay? So here you go. We have all those forces now being applied to this object. We can also define, we can also ask, I can also ask you, what's the work of the net force? We can also do that. Okay? We can have work done by this force F. We can have the work done by the weight. I can ask you what's the work done by the normal. I can ask you what's the work done by the force of friction. But I can also ask you what is the work done by the net force, by the sum of all those forces. It's also possible to ask you that. Make sense? Okay? And there is important consequences, okay, for this type of definition. And you're going to see why. Again, the concept of work is strictly connected with the idea of energy. It is work that defines energy. Okay, we start with the definition of work, and then from the definition of work, we discover that there is something important associated with work that we call energy. That's how it goes. Let me see if we have. Oh, here you go. Net force. Okay. Yeah. Okay. So let's write that down here. Not this one here. Okay. Let us talk about work now. Let us talk about work now. Mathematically speaking, work is defined for a given or a set for a given force, let's say for a given force or a set of forces. Okay? The mathematical definition of work for a uniform force is the simplest definition of work. Mathematical definition of work for a uniform force F is work done that you go work done by a given force F. Oops. Work done by a given force F is going to be what? You know, the magnitude of that force magnitude of the force times the magnitude of the displacement. I'm gonna put it like delta x. I'm gonna put x here, and can be a vector. The displacement can be a vector as well. Delta. And what? The cosine of the angle between the force and the displacement. Accent function. Right in here. Cosine of the angle between the force and the displacement. I'm going to denote like that. And this angle is taken whenever the two vectors are tail to tail. Okay? This angle, the above angle, is measured, is determined whenever the two vectors are placed the above angle. Let's see where the above angle, where the angle is given, where this angle, whereas this angle, let me see how I'm going to write that down here. Whereas this angle is the angle, between the vectors when they are positioned tail to tail. Every time that you measure an angle between vectors, you always take that with the vectors, placed tail to tail. Okay? So here in this drawing, let's take a look at this drawing right in here. Right in here in this drawing, the angle theta between this force and the displacement is going to be this angle right in here. Okay, when you place the vector force tail to tail with the vector displacement. That's how you measure the angles in physics. Okay, so here we go. Let's see. Let's take a look at some examples, right? Here we go. Oh, if the force is not uniform, then what do we do? We apply an integral. Okay. This type of integral you should have seen already, right? Is a path integral. Okay. If the force is not uniform, right? The force is not constant nor uniform, then we have to redefine the above in terms of an integral. F cosine, you still have the cosine of theta, and the delta x becomes dx. It's taken from the initial position to the final position. Okay. Now, because of this type of operation that you see there, we can define something else that we call the scalar product. Okay. And we're going to use it. There's a useful type of product operation with vector. Okay, so here you go. Now is a good moment to define a new vectorial operation. Okay, the scalar product. Okay, the scalar, this product maps two vectors into one scalar. That's what it is. This product transforms, right? That's better to write that down. Transforms two vectors into one scalar. Okay, so here you go. If you have two vectors, A and B, assume that you have two vectors A and B. Here you go. The scalar product between those two vectors, A and B, here you go. Yeah, take it out. Is denoted A. Okay, the scalar product is represented by a dot. Let's see if I can find a dot here. Okay, this dot here is better. Here we go. That's how we represent the scalar product. We're gonna write that down here. B. Suppose you have two vectors, right? A and B. You can operate between those two vectors as a scalar product. And by definition, A dot B is going to be what? It's going to be the magnitude of A, the magnitude of B, times the cosine of the angle between A and B. Okay? So I'm going to write that down here also, A and B. A, comma B. And again, those two vectors must be placed tail to tail. Right? A and B. Here we go. If you want to simplify that, just put theta in there. And it stays subintended that the two vectors must be aligned tail to tail. So what you see right in here, from the definition of force, oh, what do I have here? It's not supposed to have this thing here, right? Here you go. From the definition of work, we can see that the work done by a given force is what? Is the scalar product between F and delta X. Go. F and delta X. Similarly, for a non-uniform force, okay, the work done similarly, what time is 6:30? Oh, for non-uniform force, here we go. The work done by that force is going to be the integral of the force dx when you displace from the initial position to the final position. The final position. We can here write that as, how do you can here write that too? In terms of the scalar product. In terms of the scalar product, we can here write that as being F dot dx, the vector dx. I'll write that down as the vector dx. Okay? And in this case, because now I'm writing the vector dx, I have to redefine here my limits. My limits now needs to be here written as vectors as well. Because we are integrating over a vector, the limits should also be integrated. Okay, here we go. Good. X naught, the vector xf. Have you seen that? Path integral. Which, by the way, can be broken down into three integrals. Into the integrals of three components. Okay, so fx dx, I'm gonna put here fx dx plus fy dy plus fz dz. Okay, here we go, x naught to xf, scalar x naught to scalar xf. Now there is no need to have a cosine theta there. Here is going to be fy dy fz. I'll change the limits very soon, hang in there. Oh man, what did I do there? Huh. Hey, where's the integral? Here we go. Now let's put it here. Okay. Here is going to be dz. Oh, huh. Why is it doing that? fdz. Change it here. fy dy. Oh, there. Here you go. Oh, you got the idea, right? I'm spending too much time doing that. Okay, so that's what we have here. Let's start. What time is that? 6:36. Let's see if we have time to do an example. Okay. Oh, you gotta start working with dot products, right? Here you go. How do we? Okay. So here you go. That's the definition of dot product. Okay, that's the definition of dot product. Magnitude of A, magnitude of B, cosine of theta between the two angles. And we can commute those two, because those two values are scalar, we can commute them, and we can prove that A dot B is equal to B dot A. Okay? The dot product is commutative. So that's where everything starts. Everything starts with this definition here. Everything starts with this definition here. What we discover from this definition is that not only the dot product is commutative, but it also has a distributive property as well. Okay, all of those come from the definition there. Magnitude of A, magnitude of B, cosine of theta. What else? Another property of A dot B. Another property of the A dot B is that if the cosine, or if the angle of those two vectors is 90 degrees, just like you saw before, A dot B is going to be what? It's going to be 0, right? Just like you saw for the work done by the weight and the normal. What else? What else do you discover? Okay, if A and B are parallel to one another, now the angle between them is 0 degrees. So A dot B is going to be magnitude of A times magnitude of B. Similarly, if those two vectors are anti-parallel, then the A dot B is going to be a minus the magnitude of those two vectors. Those are just consequences of the definition of the scalar product. What else can you have here? Here you go. For the unit vectors, we have something like that, right? X hat is equal magnitude of x hat equal magnitude y hat equal to magnitude of z hat is equal to 1, right? So because they are perpendicular to one another, x hat dot y hat is going to be 0, right? And now that we have this, not only x hat dot y hat is going to be 0, but x hat dot x hat is going to be 1, and so on. Now, with all those consequences worked out, let's see which other way we can here write a dot b. Let's see which other way we can here write a dot b, okay? Hi.
Hey, how you doing? Good evening.
Good evening.
Can I make one announcement?
Yeah, go ahead.
Hey, look, ladies, gentlemen. Okay, everybody's over 21. This is a college. We don't play no kiddie games up in here. Okay, when y'all use my restrooms, no water bottles on my toilets. Take all your goodies with you, please. Everybody's of age in here. Everybody knows. Not saying that this is you guys. Okay? Okay?
Yeah.
Thank you, ladies and gentlemen. Thank you, sir.
Okay. Okay. Here you go. We're almost over here. So I'm gonna, take a look at this. Let's take a look at this dot product here, using all those properties that we are talking about. Right, here you go. I'm gonna do that for you. We have what? 5 more minutes to do. We have 10 more minutes to do that. We can do that. Here you go. I'm gonna get this guy here. That's the definition, right? That's the definition of the dot product. But we can write this dot product in another way as well. Here you go. Okay, remember, I'm gonna erase the stuff here. Here you go. I'm gonna get a parenthesis. Consider that a type of example, right? Example, prove that a dot b is equal to ax times bx plus ay times by plus ay times b plus az times bz, okay? Consider that as though it's an example like that. Here you go. I'm going to put it here, ax. It's going to be ax, b ay, by, right? B, ay, az. Here you go. A, x, a, y, a, z. And now I'm going to put b here. There's one more thing that needs to be done. What's missing here from this equation that I didn't put there? What's missing from this equation? The x hat, right? Here you go. Let's put the x hat here. No. This one. Okay. A x hat. Y hat. And z hat. So here we go. Now all I have to do is to write down bx, by, and bz. Okay, so what we're going to do here? We're going to apply the distributive property of that we proved before. Okay, so we're gonna rewrite that in terms of ax x hat dot what we have here. Oh, one more. This one. What else? Okay, plus I'm gonna get this one here. 644 ay times everybody else here. Okay, I'm gonna take this one out. Okay, here we go. And az z hat dot all that stuff. Go like that. Okay, applying the distributive property. Distributive property. Right? We're going to apply the distributive property again. Because now what is outside the parentheses must go inside the parentheses. Take it out. Go ahead, do that yourself. Here you go. Distribute here. Distribute here. Distribute here. Alright. Oops. Did it. Something wrong here. Yeah, right in here. Alright. And we do for the same for the others. What happens? This guy here, this x hat dot x hat is gonna be 1, right? Okay, so here we go. We're gonna do just for the first term, and the other terms follow suit. The other terms just follow suit. Here we go. This one here, x hat dot x hat is 1. This one, x hat dot y hat is what? Huh? Two vectors perpendicular to one another. What is equal to? 0. And the other, you know, x hat dot z hat is what? 0 as well, right? So what do we have? We have next line. We go. We have this becomes 1 ax bx. This becomes 0 because they are perpendicular. And same thing happens to the other terms, right? So we end up with ax bx plus ay by plus az bz. Okay, so that's a very useful relation that we are going to be using throughout the semester. Okay, so that's what we have. Oh, no. Let's go 6:48. Let's go upstairs for our lab. And We'll continue with that next lecture, next week. Okay, thank you for being here.